What if the universe itself had an expiration date? Picture this: a cosmos where stars don't just fade, but time itself unravels, where every moment we've ever known collapses into an unfathomable nothingness. This isn't just science fiction, it's one of the most profound mysteries haunting physicists and philosophers alike. The end of time isn't just about clocks stopping, it's about the very fabric of reality dissolving, leaving us to wonder, what does it mean for existence to simply stop? For centuries, humans have grappled with the idea of finality, whether through myths of apocalyptic fires or religious visions of divine judgment. But modern science takes this question to a staggering new level. What if the laws of physics themselves predicted our universe's demise? From black holes swallowing reality to strange quantum fluctuations rewriting the rules of existence, the theories are as wild as they are terrifying. And yet, hidden in these ideas are clues not just about how the cosmos might end, but about the nature of time itself. Is it a river flowing endlessly, or a thread that could snap without warning? That's the journey we're embarking on today. Over 30 breathtaking theories, each one a window into the unimaginable. Some will sound like nightmares ripped from the depths of space, while others feel almost poetic, like the universe sighing its last breath. But one thing ties them all together. They force us to confront the fragility of everything we know. So settle in, because we're about to venture beyond the edges of human understanding, into the abyss where time itself may meet its ultimate fate. The answers, if there are any, will change how you see reality forever. The first chilling possibility on our list is the Big Crunch, a cosmic doomsday where the universe doesn't just fade away, but violently recoils into itself. Imagine every galaxy, every star, even the atoms in your body hurtling backward through time, squeezed into an infinitely dense point. It's the Big Bang in reverse, a catastrophic collapse where gravity, the very force that holds planets together, becomes the universe's executioner. For decades, scientists thought this might be inevitable. After all, the universe is expanding, but what if gravity is like a rubber band stretched too far? Eventually, it could snap everything back. Picture galaxies merging into a single, searing mass, space-time crumpling like paper tossed into a fire. Even black holes would be ripped apart in the final moments, their monstrous appetites no match for the crushing weight of reality folding in on itself. But here's where it gets even stranger. Some models suggest this collapse wouldn't just be an ending, it could be a reset. A cosmic rebirth where the singularity sparks another Big Bang, birthing a brand new universe. It's a hauntingly beautiful idea that our cosmos might be one link in an endless chain, expanding and collapsing in an eternal loop. Yet modern observations cast doubt on this theory. Dark energy, the mysterious force accelerating the universe's expansion, seems to be winning against gravity's pull. If it keeps pushing galaxies apart faster and faster, the Big Crunch might never happen. But don't rule it out just yet. Some physicists speculate dark energy could weaken over time, or that unknown forces might still trigger collapse. After all, the universe loves surprises. One thing's certain, whether it's destined to crunch or not, this theory forces us to confront a profound truth. Time might not be an arrow flying endlessly forward. It could be a pendulum swinging between creation and destruction in a dance older than existence itself. The Big Crunch paints a dramatic finale for our universe, but is there any real evidence to support it? Let's peel back the layers of this cosmic debate, starting with the afterglow of creation itself, the cosmic microwave background, or CMB. This faint radiation left over from the Big Bang is like a fingerprint of the early universe. Scientists studying its subtle irregularities initially thought they'd found clues pointing toward an eventual collapse. Tiny fluctuations in temperature and density seemed to hint that gravity might one day overpower expansion, pulling everything back together. But then came the bombshell discovery of dark energy in the late 1990s. Imagine pouring gasoline on a fire. That's essentially what dark energy does to the universe's expansion. Observations of distant supernova revealed that not only is the cosmos growing, it's accelerating faster and faster, as if some unseen force is stretching space-time itself. This threw the Big Crunch theory into serious doubt. Suddenly, the rubber band analogy didn't hold up. The universe wasn't slowing down. It was sprinting toward what some call the Big Freeze, where galaxies drift so far apart that the night sky goes dark forever. Yet not all physicists are ready to dismiss the crunch. A vocal minority argues that dark energy might not be constant. It could weaken over billions of years or even reverse its effects entirely. Picture a car's accelerator pedal slowly lifting. Expansion might eventually plateau, allowing gravity to regain control. Some models even suggest dark energy could behave like a cosmic switch, flipping from repulsive to attractive, triggering collapse. It's a long shot, but as one researcher put it, the universe has a habit of humbling our assumptions. Then there's the curious case of the CMB's so-called cold spot, a mysterious region of space where temperatures dip unexpectedly. Could this be an artifact of an earlier cosmic contraction, a scar from a previous cycle in an endless loop of bangs and crunches? The data is contentious, but it keeps the door open for theorists who believe our universe might be trapped in a cycle we don't yet understand. So where does that leave us? The scales currently tip toward an endless expansion. Dark energy seems relentless, but science thrives on unanswered questions. Perhaps the most fascinating takeaway isn't which theory wins, but what this debate reveals about time's nature. Whether the universe collapses or flies apart forever, one truth remains: the ultimate fate of reality is written in forces we're still learning to measure, let alone comprehend. If the Big Crunch is the universe collapsing in on itself like a deflated balloon, then heat death is the opposite, a slow, silent fade into nothingness. Picture a cup of hot coffee left on the counter. At first, it's steaming, full of energy, but over time, that heat spreads out until the coffee is the same temperature as the room. Now imagine that same principle applied to the entire cosmos, where every star, every galaxy, even the last flickers of radiation, eventually cool into a lifeless, uniform chill. This is the fate many physicists consider most likely, a universe not with a bang but with a whimper. Entropy, the natural tendency of things to move from order to chaos, holds the key to this grim scenario. Think of it like a wind-up toy. At first, it's full of energy, darting across the floor with purpose, but as the spring unwinds, the movement's slow until finally it stops completely. The universe works the same way. Stars burn through their fuel, galaxies exhaust their gas clouds, and even black holes, those cosmic vacuum cleaners, aren't eternal. Over trillions upon trillions of years, they'll leak away through a process called Hawking radiation, vanishing like smoke in the wind. What's left? A vast, dark sea of particles so spread out that no two will ever collide again. No new stars will ignite, no planets will form, and the temperature will inch closer and closer to absolute zero, the point where all motion ceases. Time won't end in the traditional sense, but it might as well. With no energy differences to drive change, the universe becomes a static wasteland, an endless expanse where nothing ever happens again. But here's the twist: this process isn't just about things running down, it's about the very laws of physics ensuring there's no way back. Like a shattered glass that can't reassemble itself, the universe will reach a point of maximum entropy where every possible outcome has already played out. Some simulations show galaxies stretching into faint, ghostly tendrils, their light redshifted into oblivion, while black holes glow dimly before winking out one by one. It's a poetic kind of doom where even the mightiest structures submit to the inevitable. Yet even in this bleak vision, there's room for wonder. The sheer scale of time involved is mind-bending. Heat death wouldn't happen tomorrow, or in a billion years. We're talking timelines so vast they make the age of the universe look like a blink. And some theorists speculate that in this frozen, equilibrium state, random quantum fluctuations could, against all odds, spawn new universes. A single, improbable twist in the void might birth another Big Bang, resetting the cosmic clock. So while heat death paints the coldest possible ending, it also reminds us of something profound. The universe isn't just dying, it's transforming in ways we're only beginning to grasp. And in that transformation, there's a strange, haunting beauty. The idea that even in the deepest freeze, the seeds of something new might still lie hidden, waiting for their moment to reignite. Heat death might seem like the universe's final, frozen verdict, but what if nature itself has a wild card up its sleeve? Enter quantum fluctuations, the subatomic loopholes that could rewrite the rules of cosmic fate. At scales smaller than atoms, particles don't behave like billiard balls. They pop in and out of existence unpredictably, governed by chance rather than certainty. And in a universe stretched thin by heat death, these tiny irregularities could become cosmic game changers. Take quantum tunneling, a phenomenon so bizarre it feels like magic. Normally, if you throw a ball at a wall, it bounces back. But in the quantum realm, there's a tiny chance the ball could suddenly appear on the other side, as if the wall wasn't even there. Now picture this playing out across eternity. In a cold, empty universe, even the tiniest chance becomes inevitable given enough time. A random quantum fluctuation could tunnel into a bubble of new energy, sparking a fresh Big Bang in the void. It's like a single ember reigniting a dead fire against all odds. Reality might reboot itself. Then there's the mind-bending concept of Boltzmann brains. Named after a 19th century physicist, these aren't literal brains but hypothetical self-aware structures that could form purely by chance. Imagine particles randomly arranging themselves into a conscious entity complete with false memories of a past that never existed. In a universe where time stretches infinitely, the improbable becomes unavoidable. Statistically, it's more likely for a lone, floating brain to spontaneously assemble than for an entire universe to re-emerge. So which is more plausible, that we're living in a genuine cosmos or that we're fleeting hallucinations in an eternal abyss? Recent studies on vacuum decay add another layer to this puzzle. Our universe might be sitting in a false vacuum, a seemingly stable state that's actually a hair's breadth from collapsing into a lower energy reality. If this quantum phase transition occurred, it would create an expanding bubble of new physics, obliterating everything in its path at the speed of light. One paper suggests this could happen anywhere, anytime, with no warning. The twist: some models propose that such an event might not be destruction but transformation, a reset button for physical laws themselves. So where does that leave heat death? Even in the coldest, darkest future, quantum mechanics whispers a tantalizing possibility. Nothing is truly final. The universe might not die so much as a stutter, a flicker in the dark, a rearrangement of the cosmic deck. Whether through spontaneous rebirth or eerie Boltzmann illusions, the end could just be a doorway we don't yet understand. And that's the real lesson here when it comes to time's ultimate fate. Even the laws of physics keep a few secrets up their sleeves. The Big Crunch and heat death offer two extremes, collapse or freeze, but there's a third option that's far more violent. Imagine dark energy, the force accelerating the universe's expansion, growing stronger over time. Not just pushing galaxies apart, but amplifying until it overpowers every binding force in existence: gravity, electromagnetism, even the nuclear glue holding atoms together. This is the Big Rip, a cataclysm where space-time itself is shredded, leaving no structure, no matter, nothing but solitary particles hopelessly adrift in a disintegrating void. The key to this nightmare scenario lies in a deceptively simple number, the equation of state parameter, or W. In cosmology, W describes how dark energy's density changes as the universe expands. If W equals -1, dark energy remains constant, leading to heat death. But if it dips below -1, a possibility some models can't rule out, dark energy becomes phantom energy, growing denser as space stretches. Like a car's engine revving louder the faster it goes, phantom energy would drive expansion at an ever-increasing rate. First, galaxy clusters will be ripped apart, their gravitational bonds no match for the swelling void between them. Next, individual galaxies unravel, stars torn from their orbits like leaves in a hurricane. Then, planetary systems disintegrate. Earth would be peeled away from the sun in a final, silent farewell. But the horror doesn't stop there. In the last moments, planets and stars themselves explode as the forces binding their atoms surrender. Even atomic nuclei would be split apart, protons and neutrons ripped from each other in a subatomic apocalypse. The very fabric of space-time, stretched beyond its limits, might fracture like glass under pressure. Sound impossible. The terrifying truth is we don't know. Measuring W with precision is one of cosmology's greatest challenges. Observing distant supernova or the cosmic microwave background provides clues, but phantom energy's effects would be subtle until it's too late. Some theorists argue quantum gravity effects could halt the rip at the last instant, while others suggest it might expose deeper layers of reality, like a canvas tearing to reveal the frame beneath. What makes the big rip so unsettling isn't just its brutality, but its inevitability if W crosses that critical threshold. Unlike the slow fade of heat death, this would be a crescendo of destruction, a definitive end where time itself loses meaning. No cycles, no resets, just an empty stage where the universe once performed. Yet even here, there's a haunting question. If space-time can be torn, what lies on the other side? The answer, like dark energy itself, remains one of cosmology's most chilling mysteries. Phantom energy doesn't just threaten the universe with a big rip. It could transform cosmic doom into something eerily precise, a countdown clock for reality itself. Imagine knowing the exact date when Earth would be torn apart, atom by atom, as phantom energies grip titans. Some models suggest this isn't just theoretical. If certain conditions hold, the end could arrive in as little as 22 billion years. That might sound unfathomably distant, but on cosmic scales, it's a ticking timer with terrifying clarity. The math behind this apocalypse hinges on phantom energy's equation of state specifically. If its parameter, W, dips just slightly below -1. Even a tiny deviation, say -1.01, would be enough to trigger a runaway effect. As space expands, phantom energy's density grows exponentially, like a snowball rolling downhill, gathering mass until it becomes an avalanche. Researchers have mapped this escalation in chilling detail. First, galaxy clusters separate in about 10 billion years, then the Milky Way unravels 5 billion years later. Earth's final hour would come roughly 3 months before total annihilation, when the sun's gravity can no longer hold our planet in orbit. In the last minutes, continents would fracture as tectonic forces fail, and in the final microseconds, atoms themselves explode outward. But here's where the controversy ignites. Not all physicists buy into phantom energy's doomsday math. Critics argue that these models rely on extrapolating dark energy's behavior far beyond what we've observed. It's like predicting a hurricane's path using only the first breeze possible, but riddled with uncertainty. Others point to quantum gravity effects that might kick in at Planck-scale densities, acting as cosmic circuit breakers to halt the rip. Then there's the Big Bounce hypothesis, where phantom energy's collapse triggers a new Big Bang instead of oblivion. The debate isn't just academic, it's a race to understand whether the universe's fate is written in stone or scribbled in vanishing ink. What makes this countdown so haunting isn't just the precision, it's the paradox. If phantom energy is real, we're living in a universe with an expiration date, yet one so distant it feels abstract. But consider this, 22 billion years is barely a blip compared to the near-infinite timelines of heat death. In a way, the Big Rip is almost merciful, a swift, decisive end rather than an eternal fade. And that's the real spine-tingling revelation. Time might not just end. It could have a finale, scripted down to the last second by forces we're only beginning to measure. The Big Rip offers a violent, if predictable, demise, but what if the universe's end comes not from external forces, but from a flaw buried in the fabric of reality itself? Enter vacuum decay, a doomsday scenario so abrupt it could rewrite the laws of physics in an instant. Picture this, a tiny bubble of true vacuum forms somewhere in space, its walls expanding at the speed of light. By the time we detected it, the bubble would already be upon us, erasing everything we know, not just matter, but the very rules that govern existence. This nightmare stems from an unsettling possibility. Our universe might be sitting in a false vacuum, a seemingly stable state that's actually as fragile as a house of cards. Think of it like a valley surrounded by mountains. We're sitting comfortably at the bottom, unaware there's a deeper valley below. If something knocks us over the ridge, a quantum fluctuation, a high-energy collision, we'd tumble into that lower energy state, triggering a catastrophic phase transition. The Higgs field, which gives particles their mass, could be the culprit. Experiments at CERN hint it might not be in its lowest possible energy configuration, meaning our entire reality is fundamentally temporary. The moment decay begins, the effects would be unstoppable. Inside the bubble, particles would gain new masses, forces would behave differently, and atoms as we know them might cease to exist. Chemistry, biology, the very structure of matter, all of it rewritten in a flash. The scariest part, we wouldn't see it coming. The bubble's edge moves at light speed, granting no warning. One moment, Earth exists, the next, it's an alien landscape governed by unfamiliar physics, if it even remains solid at all. Yet there's a bizarre silver lining. Some models suggest vacuum decay might not destroy everything, just transform it. A new universe with different constants could emerge from the wreckage, like a phoenix born from the ashes of the old. Others argue this might already have happened before, that our cosmos is the aftermath of an earlier vacuum collapse. The chilling takeaway, we might be living on borrowed time, in a universe that's one quantum hiccup away from reinventing itself. So while black holes crush and dark energy stretches, vacuum decay lurks as the most insidious threat, an end not from outside forces, but from the invisible scaffolding of reality itself. And that raises a haunting question. If the universe can unravel this easily, how many times has it already happened? Vacuum decay threatens to rewrite reality from within. But what if our universe is just one fragile bubble floating in an endless sea of creation? This is the mind-bending premise of eternal inflation, a theory where the cosmos isn't just expanding but multiplying. Picture a boiling pot of water with steam bubbles constantly forming, growing, and sometimes colliding. Now imagine each bubble is an entire universe inflating at unimaginable speeds, while new ones keep budding off endlessly. Our entire reality might be a single froth on this cosmic brew, utterly unaware of the infinite others beside it. The roots of this idea trace back to physicist Alan Gough's groundbreaking work in the 1980s. He realized the early universe didn't just expand, it underwent a hyperfast inflation, doubling in size every tiny fraction of a second. But here's the twist, inflation might not have stopped everywhere. Like a wildfire that can't be fully contained, pockets of space could keep inflating forever, while others, like our universe, slow down and settle. This means the greater multiverse resembles a fractal, with island universes constantly sprouting, each with its own unique laws of physics. Some might have stronger gravity, others no stars at all, and a few could be so alien that time itself flows backward. The implications are staggering. If inflation is eternal, then beginnings and endings lose their meaning. While one universe collapses into a big crunch, another is being born in a distant corner of the multiverse. Time doesn't end, it just becomes local, like weather patterns on different planets. Our cosmic bubble might freeze in heat death, but elsewhere, inflation keeps churning out new realities like an unstoppable assembly line. But how could we ever prove this? Some researchers hunt for bruises in the cosmic microwave background, anomalies that might mark where our bubble universe grazed another. Others simulate quantum fields to see if eternal inflation naturally emerges from the math. The hardest pill to swallow. If true, we're trapped in our pocket of space-time, forever cut off from the multiverse's infinite variety. It's like being stuck on one page of an endless book, knowing you'll never read the rest. Yet there's a strange comfort in this theory. Even as our universe ages toward darkness, the greater multiverse thrives, endlessly creative. Time's arrow might not point toward doom, but toward an unfathomable tapestry of realities, each with its own fate. So while eternal inflation doesn't promise immortality for us, it hints at something grander, a cosmos where endings are just illusions and beginnings never cease. What if the universe doesn't end at all, just hits the reset button over and over in an infinite loop of rebirth? This is the radical vision of Roger Penrose's cyclic conformal cosmology, or CCC, a theory so audacious it rewrites not just the fate of the cosmos, but the nature of time itself. Picture a universe where black holes don't just vanish, they become cosmic erasers, scrubbing away all traces of the past to make room for a new beginning. No Big Bang, no heat death, just an endless cycle where each eon gives way to the next in a silent, seamless handoff. At the heart of CCC lies a mind-bending tool, the conformal diagram. These aren't your typical maps of space and time. They're warped, stretched representations where infinity gets folded into a finite frame. Imagine taking the entire lifespan of the universe, from explosive birth to cold, empty death, and squeezing it onto a single sheet of paper. In this twisted geometry, the far future of one eon becomes indistinguishable from the Big Bang of the next. Gravity weakens, particles lose mass, and the universe stretches into a featureless void only to rebound, conformally rescaled into a fresh cosmos. It's like a movie reel where the final blank frame suddenly cuts to a new opening scene. But how does history get erased? Enter black holes and Hawking radiation. As black holes evaporate over eons, they release their trapped information back into the universe, or so we thought. Penrose flips this idea on its head. In CCC, that radiation doesn't just leak out, it vanishes entirely, taking with it all records of the past. Black holes act like cosmic shredders, ensuring no star, no galaxy, no trace of the previous eon survives to clutter the next. The universe isn't just recycled, it's sanitized, rebooted with a clean slate. Not everyone's convinced, of course. Critics argue that quantum mechanics forbids such total information loss, a cornerstone of modern physics known as unitarity. If Hawking radiation preserves information, as recent firewall paradox research suggests, CCC's elegant cycle collapses. Others point to the cosmic microwave background, searching for Hawking points. Circular imprints Penrose claims are echoes of ancient black holes from prior eons. The evidence is contentious, with some calling it statistical noise, while others see tantalizing hints of a deeper truth. What makes CCC so thrilling isn't just its defiance of entropy, but its poetic elegance. Time isn't linear, it's a Möbius strip twisting back on itself in ways that defy intuition. And if Penrose is right, our universe isn't headed for oblivion. It's just one page in an infinite cosmic story, where every ending is secretly a new beginning. What if our universe is nothing more than a cosmic projection, a hologram so vast we mistake it for reality? This isn't the plot of a sci-fi movie. It's a genuine hypothesis born from string theory's most radical idea, the holographic principle. Picture reality as a colossal computer simulation where every star, every atom, even your thoughts, are just pixels encoded on a distant two-dimensional surface. But what happens when the code breaks? Some physicists warn that spacetime itself could pixelate, glitching into oblivion like a corrupted video file, and shockingly, we might already have seen the first signs. The holographic principle flips everything we know about reality on its head. Normally, we think of the universe as three-dimensional, up and down, left and right, forward and back. But this theory suggests all that depth is an illusion, a shadow cast by information etched onto a flat boundary at the edge of existence. It's like watching a 3D movie without the glasses. The depth feels real, but it's just a trick of light. In this view, black holes are the ultimate data compressors, squeezing three-dimensional information into two dimensions without losing a single bit. Now imagine a flaw in that cosmic compression. If the hologram stutters, if the data stream from the edge of the universe gets interrupted, spacetime could start unraveling. Gravitational waves, those ripples in the fabric of reality detected by LIGO, might hold the first clues. Some researchers speculate that certain anomalies in the data resemble digital artifacts, as if the universe's rendering engine briefly lagged. One bizarre event, labeled GW150914, showed a signal that didn't match any known astrophysical source. Could this have been a flicker in the hologram, a bug in the cosmic code? The nightmare scenario, a cascade failure. If one region of spacetime degrades, the corruption could spread at light speed, rewriting the laws of physics as it goes. Matter might dissolve into blocky, pixelated fragments, like a glitching video game character. Time could stutter, skip, or freeze entirely as the simulation struggles to process its own collapse. Even stranger, some models suggest this wouldn't feel violent, more like reality gently unraveling, as if the universe was a dream you're waking up from. Yet there's a twist. Holographic glitches might not mean the end. In computing, crashes often lead to reboots. If our universe is a projection, its collapse could trigger a recalibration, a new hologram with adjusted parameters. Suddenly, the constants of nature might change. Stars could burn brighter or dimmer, and life, if it re-emerges, would evolve under unfamiliar rules. It's a haunting thought that apocalypse and genesis might be the same event, just seen from different sides of the cosmic screen. So while black holes crush and dark energy stretches, the holographic universe offers a uniquely digital demise, one where reality isn't just destroyed but debugged. And that leaves us with a spine-tingling question. If we're living in a simulation, who's holding the power button? Imagine living in a house built on a cliff's edge, one tremor away from plunging into the abyss. That's the unsettling reality proposed by false vacuum metastability, a theory suggesting our universe isn't nestled in true stability but perched on a precarious ledge. In the 1980s, physicists like Sidney Coleman realized something chilling. The Higgs field, which gives particles their mass, might not be in its lowest possible energy state. Instead, it could be trapped in a false vacuum, like a marble resting in a shallow dip on a hillside. One nudge, a quantum fluctuation, a high-energy collision, and everything could tumble into the deeper valley below, rewriting the laws of physics in an instant. The mechanics of this collapse are as elegant as they are terrifying. Quantum tunneling, normally a rare subatomic quirk, becomes the universe's undoing. Picture a snowball rolling uphill without any push, a statistical impossibility under classical physics. But in the quantum world, there's always a tiny chance. If the Higgs field tunnels through its energy barrier, it spawns a bubble of true vacuum, where particles have entirely different masses and forces behave unpredictably. This bubble expands at light speed, annihilating everything in its path. By the time you saw the wall of doom approaching, it would already be too late. The collapse doesn't just destroy matter, it redefines reality itself. Could this happen tomorrow? Particle accelerators like the Large Hadron Collider are racing to find out. By smashing protons at near light speeds, scientists probe the Higgs field stability, searching for hints of that deeper valley. So far, the data suggests our false vacuum might last billions of years, but might is the operative word. The margin for error is razor thin. If the Higgs mass is just slightly lighter than measured, or if undiscovered particles nudge its energy, the scales could tip toward catastrophe. One controversial study even suggested the LHC's collisions might, in theory, trigger the very tunneling event we fear, though the odds are vanishingly small. Yet here's the twist: if vacuum decay happened, we'd never know. The bubble's edge moves too fast for any warning. One moment the universe operates as usual, the next fundamental forces unravel. Stars wouldn't explode, they'd simply cease to exist as atomic bonds fail. Some models suggest life might persist inside the new vacuum, adapted to bizarre physics, while others predict total annihilation. Either way, the cosmos as we know it would be erased, like a sandcastle washed away by a tide we never saw coming. What makes this theory so haunting isn't just its violence, but its inevitability. If we're truly in a false vacuum, quantum mechanics dictates collapse isn't a question of if, but when. Given infinite time, even the rarest events become certain. Yet there's a strange comfort in that. If the universe is a ticking clock, at least it's one we're all sharing, a countdown written into the fabric of reality itself, silently ticking away beneath our feet. Billions of years from now, long after the last stars have burned out and galaxies have faded into darkness, the universe will enter its most enigmatic phase, the black hole era. Picture a cosmos where these gravitational monsters are the sole survivors, drifting like titanic ghosts in an endless void. With no new stars to feed them, they'll slowly consume the remnants of dead planets, dust, and even light itself, growing ever more isolated as space continues to stretch. This era won't last forever, though. Thanks to a phenomenon discovered by Stephen Hawking, even black holes are on borrowed time. Hawking radiation, the faint glow of particles escaping a black hole's crushing grip, is the key to their demise. Quantum mechanics tells us that empty space isn't truly empty, it's a seething foam of virtual particles that pop in and out of existence. Near a black hole's event horizon, these particles can become real, with one falling in and the other escaping. Over unimaginable timescales, this process siphons energy from the black hole, causing it to shrink. The smaller the black hole gets, the faster it evaporates, like an ice cube melting in reverse. A typical stellar mass black hole might take 10 to the power of 67 years to vanish, a number so vast it dwarfs the current age of the universe by trillions upon trillions of times. But here's where things get explosive. In their final moments, evaporating black holes don't just fade, they go out with a bang. As their mass dwindles to near zero, the radiation they emit spikes into a torrent of high-energy gamma rays. The last surviving supermassive black holes, having feasted on galaxies for eons, will unleash bursts bright enough to outshine the entire cosmos, brief, brilliant flares in an otherwise lightless expanse. And then nothing, no matter, no energy, just an ocean of photons stretched so thin they barely interact. Time itself might lose all meaning, with no events left to measure its passage. Yet even in this desolate vision, there's a haunting beauty. The black hole era forces us to confront a profound truth. Nothing in the universe, not even the mightiest structures, escapes entropy's grip. And in their death throes, these cosmic behemoths might offer one final revelation, a fleeting glimpse into the quantum laws that govern reality's deepest mysteries. When the last black hole winks out, the universe won't just be empty, it'll be silent in a way we can scarcely fathom, as if the cosmos has finally exhaled its last breath. What if time isn't just a one-way street? Picture a shattered teacup suddenly pulling itself back together, cracks vanishing as porcelain shards leap from the floor to reform in your hands. Smoke pours back into a cigarette, flames retreat into logs, and the entire universe seems to exhale in reverse. This isn't just a rewound video, It's the mind-bending premise of time's arrow reversal, where entropy, the force driving everything toward chaos, flips direction and time itself runs backward. The concept hinges on a radical reinterpretation of the second law of thermodynamics. Normally, entropy, the measure of disorder, always increases, ensuring eggs don't unscramble and coffee never unstains your shirt. But quantum mechanics doesn't explicitly forbid entropy from decreasing. It just makes it absurdly unlikely, like flipping a coin and getting heads a trillion times in a row. Yet given enough time, think trillions upon trillions of years, statistical flukes become inevitable. Some physicists, like Oxford's David Deutsch, argue that in an infinite universe, pockets of reverse entropy must eventually emerge. In these regions, causality would appear inverted. Effects would precede causes, memories would form of the future, and aging would seem to run in reverse. Here's where it gets even stranger. If entropy reversed globally, the universe wouldn't just rewind, it would effectively reset. Galaxies would condense from scattered dust, stars would reignite, and cosmic history would replay like a film projected backward. But crucially, observers inside this reversed epoch wouldn't perceive anything unusual. To them, their present would feel as normal as ours does to us. Their past would be our future and vice versa. It's a cosmic sleight of hand where both directions of time are equally valid, just viewed from different perspectives. Not everyone's convinced, of course. Critics point out that even if entropy could theoretically decrease, there's no known mechanism to trigger such a reversal on universal scales. Others argue that the Big Bang's low entropy starting point was so specific that rewinding the tape seems impossible without a hidden law of physics we've yet to discover. Yet recent simulations of quantum systems have shown fleeting moments of entropy reversal in controlled environments, hinting that the arrow of time might be more flexible than we thought. Perhaps the most haunting implication isn't just about physics, it's about perception. If time's arrow can flip, then now is arbitrary. We might already be living in someone else's past, their future, or even a transient blip in an endless cycle of cosmic rewinds and replays. The universe doesn't need a clock, it might just be caught in an eternal dance between order and chaos, with time itself as the pendulum. Gravity keeps planets in orbit and bends starlight around galaxies, yet at the smallest scales imaginable, it might unravel the very fabric of time. Quantum gravity, the holy grail of theoretical physics, seeks to marry Einstein's general relativity with the chaotic rules of quantum mechanics. But their union comes with a bizarre consequence. Time itself might not be fundamental. Instead of a smooth, flowing river, it could emerge from something far stranger, a seething quantum foam where space and time churn like boiling water, flickering in and out of existence at scales a trillion times smaller than an atom. At these unimaginably tiny distances, the Planck length spacetime isn't smooth and continuous. It's a frothing mess of virtual black holes, wormholes, and bubbles popping into being for fractions of a second. Picture the universe's fabric magnified until it resembles the surface of a stormy ocean, with waves of probability crashing into each other. In this realm, the concept of before and after loses meaning. Events don't unfold in sequence, they fluctuate randomly like static on a TV screen. Some theories, like loop quantum gravity, suggest time is stitched together from discrete granular moments like frames in a film. Miss a frame and reality glitches. String theory goes further, proposing time might be a side effect of vibrating strings in higher dimensions, a shadow cast by deeper physics we can't yet perceive. The implications are staggering. If time is emergent, not fundamental, its disappearance at Planck scales would mean the universe's clockwork isn't just broken, it was never there to begin with. Black hole interiors might be timeless voids where cause and effect swap places. The Big Bang could be less a beginning and more a phase transition, like ice melting into water. Even our perception of time's flow might be an illusion, a trick of entropy and consciousness stitching fragmented quantum moments into a coherent narrative. Yet the most unsettling possibility is that time's dissolution isn't confined to the quantum realm. If space-time foam percolates upward, rare quantum fluctuations could erase time in localized patches. Imagine a bubble where clocks stop, aging halts, and particles freeze mid-motion, not from extreme gravity, but from the laws of physics temporarily unspooling. Some models suggest these time holes would self-heal, snapping back into continuity. But what if one grew? The result wouldn't be destruction, but erasure. A region where history, memory, and even existence itself quietly blink out, unnoticed by the wider universe. Quantum gravity doesn't just challenge our understanding of time, it threatens to erase the stage on which reality performs. And if time is an illusion, what else might be? The answer could rewrite not just cosmology, but the very meaning of now. What if our universe isn't just running on borrowed time, but on borrowed processing power? The simulation hypothesis, popularized by philosopher Nick Bostrom, suggests we might be living in an advanced civilization's digital construct, a cosmic game of The Sims with unfathomable resolution. But every simulation has an exit button. If our creators decide to pull the plug, whether to conserve resources, reboot the system, or simply because they've gathered enough data, reality as we know it could vanish in an instant like a deleted save file. Bostrom's trilemma lays out the unsettling math. Either almost all civilizations self-destruct before reaching post-human status, none choose to run ancestor simulations, or we're almost certainly living in one. The statistical weight of this argument hinges on raw computational limits. An advanced society could, in theory, simulate countless conscious beings with just a fraction of their energy reserves. Now imagine that civilization facing a system overload, or worse, losing interest. The shutdown wouldn't be dramatic, no explosions, no black holes. One moment everything exists, the next it doesn't. Poof, no traces, no artifacts, just the silent click of a cosmic end task command. Video games offer eerie parallels. When a game engine hits its memory ceiling, glitches emerge, textures flicker, physics stutter, NPCs freeze mid-action. Some theorists argue quantum indeterminacy, like the random behavior of particles in the double-slit experiment, could be our universe's version of rendering shortcuts. Even more chillingly, certain cosmological anomalies like the unexpected smoothness of the early universe mirror optimization techniques used in procedural generation to reduce computational load. But how would a shutdown manifest? One model suggests localized, blue screen failures first, regions of spacetime abruptly pixelating or repeating patterns like a corrupted video file. Others propose a more elegant exit, a graceful fade to black with consciousnesses gently dissolved before realizing anything's amiss, the darkest twist. We might never know it happened. If time itself is a programmed variable, the shutdown could retroactively erase all evidence, leaving no before to mourn the lost. Yet this theory's real horror isn't just annihilation, it's insignificance. In a multiverse of simulations, our universe might be one of trillions terminated daily, a disposable experiment in some higher dimensional lab. But here's the counterpoint that keeps physicists awake. If we are in a simulation, its creators likely encoded conservation laws to maintain immersion. Shutting it down might violate their own ethical protocols, unless, of course, we're just background characters in a universe where no one's watching. In the endless dark of a universe trillions of years past its expiration date, something impossible flickers into being, not a star, not a planet, but a lone, disembodied brain. Complete with memories, senses, even the illusion of a body it never had. This isn't science fiction, it's the Boltzmann Brain paradox, a cosmic nightmare where random quantum fluctuations birth conscious observers in the void. And the most unsettling part, statistically, it's far more likely than you existing right now in a coherent, ordered universe. The paradox takes its name from 19th century physicist Ludwig Boltzmann, who first grappled with a haunting question: why does our universe appear so organized when disorder is the default? His answer: pure chance. Given enough time, and we're talking timescales so vast they make the age of our universe look like a single tick of a clock, random particles will eventually arrange themselves into any configuration, no matter how improbable. Most of these configurations are chaotic nonsense, but occasionally, against all odds, they'll form something recognizable, like a fully functional human brain, complete with fabricated memories of a past that never existed. Picture this: in the heat-death era, when the cosmos is a thin soup of particles barely interacting, a single proton and electron accidentally collide in just the right way. Then another and another. Over quintillions of years, these chance encounters build atoms, then molecules, until, snap, a self-aware structure materializes from the void. It remembers growing up on Earth, falling in love, watching sunsets that never actually happened. It might even recall studying the Boltzmann Brain paradox itself, only to realize with horror that it's the very anomaly it once theorized about. The implications unravel reality as we know it. If Boltzmann brains are inevitable given infinite time, then statistically, you're almost certainly one of them. After all, it's infinitely more probable for randomness to conjure a single conscious observer than an entire 13.8 billion-year universe with galaxies, planets, and billions of real people. Some cosmologists see this as a fatal flaw in our models, a sign that something's deeply wrong with how we understand time, probability, or quantum mechanics. Others argue it's proof we live in a multiverse where low-entropy pockets like ours are shielded from the chaos. But the real terror isn't just existential, it's experiential. How could you ever prove you're not a Boltzmann brain? Every scientific experiment you perform, every memory you trust could just be part of the illusion. Like a dreamer who suddenly questions whether they're asleep, the paradox pulls the rug out from under reality itself. And that's the chilling beauty of it. In a cosmos without end, even the impossible becomes inevitable. You might be the real deal or just a flicker of consciousness in the dark, destined to dissolve as suddenly as you appeared. The universe won't tell you which. It just keeps rolling the quantum dice, eternally indifferent to the stories those dice invent. Black holes might not be cosmic dead ends. They could be birthing chambers for entirely new universes. That's the radical proposition of physicist Lee Smolens's cosmic bounce theory, where every black hole collapse spawns a fresh cosmos in its wake. But there's a haunting catch. Each new universe inherits slightly less information than its parent, like a fading photocopy of reality. Picture Salvador Dali's melting clocks, their surfaces dripping into oblivion, except here, it's causality itself that's slowly dissolving over eons of rebirth. At the heart of Smolens's idea lies a startling twist on Darwinism. Just as biological evolution favors traits that enhance reproduction, Smolens suggests universes could evolve to maximize black hole production. Each new cosmos tweaks the fundamental constants: gravity's strength, the speed of light, incrementally optimizing for more prolific black hole formation. Over countless cycles, universes that birth the most black holes dominate the multiverse landscape. It's survival of the fittest on a cosmic scale, with black holes as the reproductive organs of spacetime itself. Yet something insidious happens with each bounce. Quantum information, the precise states of particles, the history of galaxies, even the memory of your morning coffee, doesn't perfectly transfer between universes. Like a game of telephone played across dimensions, subtle errors creep in. Entropy increases, coherence frays, and the new universe emerges with slightly degraded physics. At first, the changes are trivial. Maybe electrons wobble a fraction more in magnetic fields. But over trillions of iterations, the decay compounds, stars burn cooler, chemical bonds weaken, and time's arrow begins to stutter. Imagine a clock whose gears gradually warp. At first, it loses seconds, then minutes, until finally, the hands spin aimlessly, unmoored from any meaningful sequence. That's the fate of causality in Smolens's model, a slow unraveling of cause and effect. Black holes in later generation universes might evaporate asymmetrically, or quantum entanglement could fray at macroscopic scales. Eventually, the cosmos becomes a surrealist painting where events don't quite chain together logically, and particles remember their histories in fragmented, dreamlike ways. Critics pounce on this information loss as a violation of quantum unitarity, a sacred law stating information can never be destroyed. But Smolens counters that our universe's apparent consistency might just be luck. We could be early in the cycle before decay becomes obvious. Others argue black holes don't vanish, they transform, imprinting their data onto the fabric of the new universe like a watermark. Recent holographic principle research even suggests information might escape black holes encoded in their Hawking radiation, potentially preserving cosmic memory across bounces. The most chilling implication: we could already be living in a degraded copy. If fundamental constants vary slightly between cycles, our universe's finely tuned physics, the exact charge of an electron, the strength of gravity, might not be perfect. They could be echoes of a more precise original, like a digital file compressed one too many times. It's a humbling thought that even the laws of nature might be subject to entropy's slow erasure, and that one day, some future universe will look back at ours as the golden age of causality before time itself began to melt. Somewhere between physics and theology lies the omega point, Frank Tipler's audacious vision of a cosmic resurrection so complete it borders on divinity. Picture this, not a quiet fade into darkness, but a universe waking up, gathering its scattered energy into a final, all-knowing mind. According to Tipler, the far future won't just be the domain of dying stars and evaporating black holes. It'll be the stage for intelligence itself to ascend, rewriting the laws of reality in its final moments. At the heart of the omega point theory is a staggering prediction. As the universe collapses toward its final singularity, what Tipler calls the Big Crunch, advanced civilizations would harness every last joule of energy to sustain themselves. Think of it as the ultimate recycling project: stars dismantled for fuel, black holes tapped for their Hawking radiation, even the vacuum of space mined for its quantum fluctuations. With infinite computational power squeezed into a finite moment, these future beings could simulate every possible configuration of matter, effectively resurrecting all who ever lived. Your thoughts, memories, even your consciousness could be perfectly recreated in a cosmic computer, less a metaphor for immortality, more a physics-backed rapture. But here's where the skeptics pounce. Lawrence Krauss, a vocal critic, highlights the glaring holes in Tipler's math. Quantum mechanics imposes hard limits on computation. No system, no matter how advanced, can perform infinite calculations with finite energy. Even if civilizations could stave off collapse, they'd eventually hit the Landauer limit, the minimum energy required to erase a single bit of information. Krauss argues that Tipler glosses over this, hand-waving the impossible with speculative physics. Then there's the elephant in the room: dark energy's relentless push. If the universe isn't destined for a big crunch but keeps expanding forever, the omega point's countdown clock never starts. Yet Tipler's defenders counter with a provocative twist. If intelligence becomes ubiquitous enough, maybe it could engineer the universe's collapse deliberately, twisting the fabric of space-time like a cosmic sculptor to trigger its own salvation. Others suggest quantum gravity effects near the singularity might permit closed time-like curves, effectively letting the future rewrite the past. It's a dizzying feedback loop where creation and observation blur into one. The omega point isn't just a theory about endings, it's a mirror held up to humanity's deepest yearnings. Whether it's a scientific inevitability or a modern myth dressed in equations, one thing is certain. It challenges us to confront what intelligence might become when pushed to the absolute edge of existence. And in that challenge, there's a strange, haunting hope that even at time's last tick, the universe might still choose to mean something. Mountains don't last forever, not even the atoms that build them. In a universe trillions of years older than today, the very bedrock of matter could crumble away silently, leaving nothing but whispers of radiation where planets and stars once stood. This is the proton decay apocalypse, a fate so slow it makes glaciers seem impatient, yet so inevitable it rewrites the meaning of permanence. Protons have long been the universe's dependable building blocks, outlasting stars, black holes, and even the stubborn grip of black holes. But what if they're not as eternal as we think? Certain grand unified theories attempts to merge physics' fundamental forces predict protons might decay into lighter particles over unimaginable timescales, around 10 to the power of 34 years. Picture a single proton in the heart of an iron atom, holding steady for eons until, without warning, it disintegrates into a positron and a pion. Now imagine that happening to every proton in existence, everywhere, all at once. First, dust particles vanish from interstellar space. Then asteroids dissolve into showers of leptons. Finally, planets and stars themselves evaporate like fog in sunlight, their mass bleeding away into a faint glow of subatomic debris. Super Kamiokande, a colossal neutrino detector buried deep beneath Japan's mountains, has spent decades hunting for this elusive decay. Its tank holds 50,000 tons of ultra-pure water, shielded from cosmic rays, where scientists watch for the telltale flash of light that would betray a single proton's death. So far, none have been caught in the act. Protons, it seems, are staggeringly stable. But absence of evidence isn't evidence of absence. If protons do decay, the process is so rare we'd need to observe countless trillions of them to spot even one event. The experiment's null results have already ruled out some versions of grand unified theories, narrowing the search for physics' ultimate rulebook. The scale of this decay is both terrifying and poetic. A proton's lifetime dwarfs the current age of the universe by a factor of 1 trillion. Civilizations could rise and fall a quadrillion times before the first proton winks out. Yet, given enough time, even the unthinkable becomes certain. In the far future, black holes might be the last structures standing, feasting on the dissolving remnants of galaxies. But eventually, they too would starve, left with nothing to consume but the fading echoes of matter that once was. There's an eerie beauty to this theory that stability itself is an illusion, a temporary state in a cosmos where even the smallest constants might be counting down. And if protons can perish, what else might be hiding an expiration date we haven't found yet? The answer could rewrite not just our future, but the laws we thought governed all of existence. Hidden in the shadows of the cosmos, something far stranger than empty space might be stirring. Dark matter, the universe's ghostly scaffolding, could be on the verge of a metamorphosis. Picture liquid helium chilled to near absolute zero, where suddenly, without warning, it defies gravity and crawls up the walls of its container. This eerie behavior, known as superfluidity, hints at what might happen if dark matter currently thought to drift unseen through galaxies suddenly undergoes its own quantum phase transition. Not a gradual shift, but a violent snap, rewriting the rules of reality in an instant. Most models treat dark matter as a passive spectator, its gravity gently shaping galaxies without interacting otherwise. But what if it's not inert? Certain theories posit a dark sector of particles and forces entirely separate from our own, governed by exotic physics we've yet to uncover. In this shadow realm, dark matter might exist in a high-energy state, like steam primed to condense into water. A slight drop in cosmic temperature or an unseen trigger could flip this invisible sea into a new phase, releasing enough energy to flash freeze the visible universe solid. The mechanics resemble how water molecules rearrange when ice forms, but with apocalyptic stakes. Superfluid helium experiments show how phase transitions can propagate almost instantly, with boundary layers spreading at velocities approaching the speed of sound in the material. Translate that to dark matter, and a transition front could surge across galaxies faster than light travels through normal space. Structures wouldn't just freeze, they'd shatter. Stars might find their orbits abruptly locked, their heat leached away by an invisible lattice. Gas clouds could crystallize mid-collapse, halting star birth entirely. Even black holes might struggle to feed as incoming matter snaps into an unchanging grid. Some physicists speculate this could explain the universe's puzzlingly low entropy at the Big Bang. A previous dark matter phase transition might have reset the cosmic clock, scrubbing away any trace of prior disorder. Others warn such an event wouldn't be survivable. As the transition propagates, ordinary matter would be caught in the crossfire. Atoms, unable to interact with the newly rigid dark sector, might find their own forces distorted. Electromagnetic bonds could fail, turning planets and flesh alike into brittle sculptures collapsing under their own weight. Yet there's a haunting counterpoint. If civilizations could detect the transition's approach, perhaps through subtle distortions in gravitational waves or anomalies in cosmic rays, they might harness it. A sufficiently advanced society could engineer localized phase states, creating impenetrable dark matter fortresses, or even weaponizing the transition itself. Like ice sculptors carving cracks to control fractures, they might guide the change rather than succumb to it. The darkest irony, we'd never see it coming. Dark matter's very nature, its refusal to emit or absorb light, means a phase shift might be invisible until its effects ripple into the visible world. By then, it would be too late to react. The universe wouldn't end with fire or ice, but with silence, as every moving part locks into place like a clockwork mechanism winding down for the last time. And in that stillness, one question would linger: was this always dark matter's destiny, or did something or someone flip the switch? What if history isn't just written in stone but etched into an infinite loop, destined to replay verbatim an uncountable number of times? This is the spine-tingling premise of eternal recurrence, where Friedrich Nietzsche's 19th century philosophical musings collide with 21st century cosmology. Imagine every moment of your life, every heartbeat, every whispered word, every fleeting thought repeating identically across unfathomable eons, not just once but endlessly, like a cosmic record stuck on repeat. The math behind this eerie idea traces back to Henri Poincaré's recurrence theorem. At its core, the theorem states that any system with finite energy and volume will eventually return arbitrarily close to its initial state, given enough time. Picture a box filled with bouncing particles. Given infinite time, their positions and velocities will realign almost exactly as they started, purely by chance. Now scale that up to the universe itself. If space-time is finite, a hotly debated assumption, quantum fluctuations could theoretically reset the cosmic clock, reconstructing every atom's position with perfect precision. But here's where physics throws a wrench into Nietzsche's poetic vision. Quantum mechanics introduces irreducible randomness. Particles don't behave like billiard balls, but like probability waves collapsing unpredictably. For true eternal recurrence, every quantum event across 13.8 billion years would need to replay identically, down to the spin of a single electron. The odds of that are so vanishingly small, they make winning the lottery every second for a lifetime seem trivial. Some theorists argue quantum decoherence erases any hope of perfect repetition, while others propose that in a multiverse of infinite parallel worlds, statistically, exact copies of our timeline must emerge somewhere. The implications ripple through philosophy like shockwaves. If the universe truly cycles identically, then every joy, every tragedy, every mundane coffee break is predetermined, not by fate but by cold, hard statistics. You'd have lived this life before and will again with no memory of the iterations. Nietzsche saw this as the ultimate test of human spirit. Could you embrace existence if told you'd relive every moment unchanged forever? Chemists, by contrast, might call it the purest absurdity, a cosmic joke without a punchline. Yet there's a haunting counterpoint buried in modern cosmology. If spacetime is a holographic projection, as some string theorists suggest, then information might be preserved at the universe's boundary like a timeless hard drive. In that case, recurrence could be less about repetition and more about retrieval. The universe rebooting from a backup, each iteration a perfect restore point. The distinction blurs between cycling and stasis, between dying and pausing. Whether you find the idea exhilarating or horrifying, eternal recurrence forces us to confront time's deepest mystery. Is the universe a one-shot experiment or a kaleidoscope rearranging the same shards of existence eternally? The answer might not lie in equations or telescopes, but in the silent spaces between heartbeats, those fleeting moments that feel, against all logic, like you've lived them before. What if reality isn't just a stage but a projection, and the projector is failing? Picture the universe as an IMAX screen stretched across the cosmic horizon, its pixels so fine we mistake them for stars. Now imagine that screen flickering, distorting, whole galaxies dissolving into jagged fragments like corrupted digital files. This isn't just a glitch, it's holographic boundary failure, a theory suggesting the universe's outer edge isn't a physical barrier, but a data storage limit approaching catastrophic overload. The holographic principle, born from string theory's most radical insights, proposes that our three-dimensional reality is an illusion, a hologram encoded on a distant two-dimensional surface. Think of it like watching a 3D movie without glasses. The depth feels real, but it's all just flat images manipulated by light. In this model, every particle collision, every supernova, even your thoughts, are just data points etched onto the universe's event horizon trillions of light years away. But data storage isn't infinite. As the cosmos expands, that horizon stretches thinner, its encoding capacity straining under the weight of 14 billion years of cosmic history. Now, the nightmare scenario: what happens when the drive fills up? At first, the effects would be subtle statistical anomalies in particle behavior, like electrons briefly forgetting their charge. Then, larger structures begin to falter. Galaxies near the observable edge might stutter in their rotation, stars flickering like faulty pixels. Gravitational wave detectors could pick up unnatural echoes, as if space-time itself was buffering. Eventually, the corruption spreads inward. Constellations fracture into blocky mosaics, their light redshifted into jagged, digital noise. The universe wouldn't collapse, it would degrade, like an aging hard drive struggling to boot. Some theorists argue we've already glimpsed this failure mode. The CMB's infamous axis of evil, a mysterious alignment of temperature fluctuations, could be the first artifacts of boundary compression. Others point to quasars whose light spectra exhibit bizarre, pixel-like discontinuities, as if their data was poorly rendered. But the real horror isn't just glitches, it's the implication that reality has a source code, and that code is running out of memory. Yet here's the twist: holographic failure might not mean oblivion. In computing, corrupted files sometimes spawn emergent phenomena, glitch art where errors become beautiful accidents. Could a faltering universe do the same? Quantum fluctuations near the failing boundary might birth surreal new physics, warping causality into Möbius strips or birthing particles with impossible properties. We might be living in the universe's blue period, where fractures in the hologram don't destroy, they transform. The most unsettling question isn't whether the screen will fail, but whether we'd even recognize it happening. If our perceptions are just decoded projections, how would we know when the projectionist walks away? The answer might lie in the quietest corners of physics labs, where the universe's pixel count is being measured, one quantum bit at a time. And what they find could rewrite not just our future, but the very definition of real. What if time itself depends on the presence of a conscious mind to witness it? This unsettling idea emerges from a radical reinterpretation of quantum mechanics, one where the universe isn't just shaped by observation but sustained by it. Picture Schrödinger's infamous cat suspended between life and death until someone opens the box. Now scale that paradox to cosmic proportions. If every quantum event requires an observer to collapse possibilities into reality, what happens when the last conscious being in the universe blinks out of existence? Could time itself unravel like an unspooling film reel, leaving only ghostly probabilities behind? The roots of this idea trace back to the measurement problem in quantum physics. At microscopic scales, particles exist in superpositions multiple states at once until observed. The classic double-slit experiment shows electrons behaving as waves when unobserved, then snapping into definite positions the moment a detector clicks. Some interpretations, like the von Neumann-Wigner hypothesis, take this further, suggesting consciousness itself is the trigger that forces quantum systems to choose a state. Extend this logic to the far future, when stars have burned out and black holes evaporated. If no minds remain to collapse quantum waves, does reality freeze in an eternal limbo, like a paused simulation waiting for input? Critics counter with panpsychism, the view that consciousness isn't unique to brains but woven into the fabric of reality itself. Rocks, particles, even the vacuum of space might possess rudimentary awareness. If true, the universe could never truly be unobserved. Every quantum fluctuation would have its own tiny witness, ensuring time's continuity. Yet even this fails to resolve the paradox entirely. If consciousness is universal but self-aware minds are temporary, does the quality of observation matter? Could a quark's faint experience sustain reality as meaningfully as a human's? The implications spiral into philosophy. If consciousness binds time, our present moment might be less a universal now and more a localized phenomenon, a bubble of collapsed reality drifting through a sea of quantum potential. Distant galaxies, untouched by any observer's gaze, could exist in a hazy superposition until their light finally reaches us. Stranger still, the act of observation might not just record history but create it, retroactively weaving cause and effect into coherence. But here's the haunting twist. If consciousness truly governs time's flow, the universe's fate hinges on the survival of sentience. Civilizations clinging to existence in the far future wouldn't just be preserving themselves, they'd be holding reality together. A single artificial mind orbiting a dying star could become time's anchor, preventing the cosmos from dissolving into ambiguity. The stakes couldn't be higher. In this view, extinction isn't just tragedy, it's the ultimate entropy, erasing not just life but the very framework of now. Whether you find this theory profound or preposterous, it forces a reckoning with our role in the cosmos. Are we passive witnesses to a pre-written script or reluctant custodians of reality itself? The answer might lie in the quietest quantum fluctuations, waiting perhaps for someone to notice. String theory paints the universe as a delicate symphony of vibrating strings, resonating through hidden dimensions we can't perceive. But beneath that elegant surface lurks a terrifying possibility. Our cosmos might be balancing on a knife's edge, one quantum hiccup away from sliding into oblivion. Among the 10 to the power of 500 possible configurations predicted by string theory, known as vacua, most are lethal. Picture a skyscraper with infinite floors, but only one safe room, our universe. Now imagine the entire building tilting, sending everything careening toward disaster. At the heart of this nightmare are Calabi-Yau manifolds, the intricate, six-dimensional shapes that determine how strings vibrate and thus dictate the laws of physics in our universe. Think of them as the universe's tuning pegs. Twist them slightly and particles gain or lose mass, forces strengthen or vanish, even time itself might stutter. In string theory's landscape of possible vacua, these manifolds aren't static. They're dynamic, warping under quantum fluctuations like rubber sheets stretched too thin. One random jostle could send our manifold tumbling down an energy slope, reconfiguring into a new, deadly stable state. The mechanics resemble a marble resting in a shallow dish. Bump it gently and it rolls back to center, but tilt the dish just slightly and suddenly the marble plummets off the edge. In cosmic terms, that tilt could be anything: a high-energy particle collision, a random quantum fluctuation near a black hole, even the cumulative effect of dark energy over eons. Once the slide begins, there's no stopping it. Space would reconfigure at light speed, rewriting physics as it goes. Atoms might unravel as electromagnetism weakens. Stars could explode or implode under suddenly altered nuclear forces, and time might fracture into disjointed fragments. Some theorists argue we've already witnessed near misses. The Higgs boson's mass hints our universe is metastable balanced, but not perfectly. Others point to anomalies in cosmic ray patterns or bizarre particle behavior at CERN as potential tremors in the landscape. The scariest part, we wouldn't see the collapse coming. Unlike a supernova or asteroid impact, a vacuum slide wouldn't cast shadows or send warnings, just an instantaneous, universe-wide reboot into a reality where life as we know it is impossible. Yet there's a haunting counterargument buried in the math. If the landscape is truly vast, with more vacua than atoms in the observable universe, then statistically, some regions must be sliding constantly. We might be living in a rare survivor pocket, insulated by cosmic luck. Or worse, we could be mid-fall, oblivious to the cliff's edge rushing toward us. The answer, like the strings themselves, remains tightly wound in dimensions beyond our grasp. Time doesn't just slow down as the universe cools, it might shatter. Picture a superconductor chilled to near absolute zero, where electrons pair up and glide without resistance, locking into a rigid crystalline dance. Now imagine spacetime itself undergoing the same eerie transition, not just freezing, but fracturing into intricate fractal patterns where moments become fixed like insects in amber. This is temporal crystallization, a theory where time doesn't merely stop. It transforms into an eternal, unchanging scaffold. The seeds of this idea sprout from laboratory oddities. When certain materials are cooled to extreme temperatures, their atoms don't just settle, they reorganize into geometric lattices, trading chaos for perfect symmetry. Superconductors exhibit this with Cooper pairs, electrons that sync up so precisely they defy entropy. Translate this to cosmology, and the vacuum of deep space, already hovering just 3 degrees above absolute zero, might be creeping toward its own phase transition. As the universe expands and cools further, quantum fields governing time's flow could lock into a lowest energy state, like a river freezing mid-ripple. Faint clues already flicker in the darkness. Astronomers have detected bizarre, fractal-like distortions in light from ancient quasars, beams that seem pixelated or unnaturally static, as if glimpsed through a fractured time lens. These could be the first shadows of crystallization creeping inward from the cosmos's edges. Meanwhile, experiments with Bose-Einstein condensates, ultra-cold clouds of atoms behaving as single quantum objects, show particles spontaneously forming crystal-like structures in time, not just space. It's as if nature keeps whispering hints of time's hidden architecture. But what would a crystallized cosmos feel like? Not sudden, but gradual, like a clock's gears slowly filling with ice. First, entropy's grip would weaken. Pendulums might swing slower, then stop mid-arc. Atomic clocks would tick erratically as time's flow clumped into discrete steps. Eventually, even quantum processes would stall, freezing reality into a tableau of infinite nows. Light itself could fracture, bending at sharp angles like a gem's facets, trapping the last photons in prism-like labyrinths. The universe wouldn't end. It would become a museum of itself, every moment preserved but unmoving. critics argue this violates relativity, which treats time as fluid and inseparable from space. Yet some modified gravity theories suggest space-time might have substructured tiny atoms of time that could, in principle, crystallize. Others counter that quantum fluctuations would always disrupt perfect order, acting as cosmic antifreeze. But the most chilling possibility, we're already inside the transition zone. If crystallization began in distant voids, its wavefront could be advancing at light speed, undetectable until it's too late to escape. The haunting beauty of this theory isn't just in its frozen apocalypse, it's in what it reveals about time's nature. We think of it as fluid, relentless, but it might be as fragile as glass, waiting for the universe's final chill to reveal its true crystalline form. And when that cold sets in, forever won't mean endless change, just a single, flawless moment held eternally still. Kurt Gödel, the mathematician who shattered our understanding of logic with his incompleteness theorems, also left a cryptic gift for physicists, a cosmic blueprint where time folds back on itself like an M. See Escher's staircase, his rotating universe model, born from Einstein's own equations of general relativity, doesn't just bend space-time, it shreds causality into paradoxical ribbons. Picture a cosmos spinning so violently that the fabric of reality twists into closed time-like curves, where your future could literally reach back and shake hands with your past. At first glance, Gödel's universe seems deceptively ordinary. Stars, planets, and galaxies still exist, all drifting through space, but hidden beneath the surface is a whirlpool of spacetime so extreme, it drags time itself into a spiral. Think of stirring honey into tea. The swirling liquid creates invisible currents that could, in theory, loop a spoon's path back to its starting point. Now replace the spoon with light, or even a spaceship, and the honey with the entire universe. In Gödel's model, if you travel far enough in any direction, you'd eventually return to your own launch pad, not just in space but in time. Your past self might watch your future self depart, trapped in an endless recursion where cause and effect trade places. The implications unravel reality as we know it. History could become a choose-your-own-adventure book where events rewrite themselves mid-chapter. Wars might end before they begin. Ancestors could inherit knowledge from their descendants, and the very concept of now would dissolve into a hall of mirrors. Gödel himself relished these paradoxes, proving mathematically that if his universe existed, time travel wouldn't just be possible, it'd be unavoidable. Einstein, though unsettled by the idea, couldn't find a flaw in the math. The equations permitted it, and the universe, it seemed, had a cruel sense of humor. But here's the catch: our universe doesn't appear to be spinning en masse. Observations of distant galaxies show no evidence of the uniform rotation required for Gödel's loops. Yet the model refuses to die quietly. Modern cosmologists note that localized regions like the swirling maelstrom around a supermassive black hole might approximate Gödel's conditions, creating microscopic time loops. Simulations using quantum gravity even suggest these closed curves could form naturally near singularities, stitching the fabric of time into Möbius strips where past and future blur. The true horror of Gödel's vision isn't the loops themselves, but what they imply about free will. If time is a snake eating its own tail, then every choice you'll ever make already exists, locked in an inescapable dance with its own consequences. Destiny isn't written in the stars, it's scribbled in the margins of spacetime's geometry. A joke only the universe understands, and that's the ultimate twist. In a rotating cosmos, the end of time isn't a finale. It's just the moment you realize you've been here before. What if death is just an illusion, not because of some spiritual truth, but because the universe's quantum rules conspire to keep you alive against all odds? This is the spine-chilling premise of quantum immortality, a thought experiment where consciousness becomes a cosmic Houdini, slipping through the cracks of doomed timelines into increasingly improbable realities. At first glance, it sounds like science fiction, but drill down into the math, and the idea takes on a disturbing plausibility. The foundation rests on the many worlds interpretation of quantum mechanics, where every possible outcome branches into its own universe. Flip a coin, and in one world it lands heads, in another tails. Now apply that to survival. If you play Russian roulette, most branches see the hammer striking the bullet, but a few defy statistics where the chamber clicks empty. Quantum immortality suggests your consciousness only persists in the timelines where you don't die. You'd never experience the end, just an unbroken chain of improbable survivals, each more baffling than the last. But here's where it escalates from eerie to outright surreal. Over infinite time, even the most ludicrous scenarios become inevitable. Imagine surviving a plummet from a skyscraper because quantum fluctuations conspired to soften your landing, or walking through a nuclear detonation as every radioactive particle improbably misses your body. The longer you live, the more the universe contorts to preserve you, bending physics like a carnival mirror. Stars might explode in just the right pattern to avoid your planet, or black holes could warp their trajectories to spare your ship. You'd become a statistical anomaly, a glitch in causality's code. Critics argue this violates the Copernican principle. Why should your consciousness be special? Yet proponents counter that it's not about privilege, it's about perspective. In an infinite multiverse, every possible observer experiences their own version of miraculous survival until their luck truly runs out. The real horror isn't living forever, but the isolation. As others perish in branching timelines, you drift into a solipsistic nightmare where reality reshapes itself around you, growing stranger with each narrow escape. The most unsettling implication: you might already be in such a timeline. Every near-miss accident, every recovery from illness could be evidence of this silent filtration process. And if true, the universe isn't just indifferent, it's an accomplice, editing your existence one quantum decision at a time. The question isn't whether you'll die, but how distorted reality will become before you finally, impossibly, do. Our universe might not be floating alone in the void. It could be one fragile sheet in a cosmic stack, waiting to smash into another reality with the force of a billion Big Bangs. Welcome to the brain collision apocalypse, where the term world-ending event takes on a terrifying new dimension literally. In string theory's wildest predictions, our three-dimensional existence is just a membrane, or brain, drifting through higher dimensional space, separated from parallel universes by less than the width of a quark. And if that gap ever closes, the resulting collision wouldn't just destroy galaxies, it would rewrite physics itself. The Large Hadron Collider has been hunting for clues of these hidden dimensions, smashing particles together at near-light speeds to search for energy that mysteriously vanishes, potentially leaking into other brains. While no definitive proof has emerged, certain anomalies in proton collision data hint at gravity bleeding into extra dimensions, as if our brain has tiny fractures. If true, it wouldn't take much to rupture those cracks entirely. A passing brain in the bulk, the higher dimensional space between membranes, could slam into ours with the unstoppable momentum of an entire reality. Visualizing this is like watching two soap bubbles collide in slow motion, but scaled up to cosmic proportions. First, gravitational distortions would ripple through space, warping starlight into funhouse mirrors. Next, fundamental forces might flicker, electromagnetism weakening, nuclear bonds straining as the brain's physics briefly merge. Then, the main event, a shockwave of pure energy, hotter than the core of a supernova, surging across the universe at light speed. Galaxies wouldn't just burn, they'd unravel, their matter reconfigured into exotic particles never meant to exist in our brain. The aftermath depends on collision dynamics. A glancing blow might leave pockets of reality intact, like islands in a flood, with survivors grappling with bizarre new laws of nature. A head-on smash could spawn a new Big Bang, rebooting the universe with different constants. Worst-case scenario, the brains stick together, crushing our three-dimensional existence into a two-dimensional plane, a cosmic pressed flower in some higher-dimensional scrapbook. Yet here's the twist: brain collisions might not be rare. Cyclic models suggest universes like ours routinely crash, rebound, and regenerate in an endless cycle. We could be living in the aftermath of the last collision, with each big bang just the echo of membranes springing apart. If so, the apocalypse isn't coming, it's just waiting backstage for its next cue. And when the curtains rise, the universe won't end with a whimper, but with a dimensional thunderclap we can't even begin to comprehend. Black holes don't just devour matter, they might be erasing cosmic history itself. Imagine a library where every book burned doesn't leave ashes, but vanishes from memory as if it never existed. This is the terrifying heart of the black hole information paradox, where the universe's most destructive objects could be triggering a slow-motion apocalypse of forgetting. According to quantum mechanics, information, the precise state of every particle, can never be truly destroyed, but black holes, those cosmic shredders, seem to violate this sacred rule. When matter falls in, its information appears trapped behind an event horizon, leaving no trace in the radiation that eventually leaks back out. It's as if the universe's hard drive is developing bad sectors, corrupting the very data that defines reality. The stakes couldn't be higher. If information is truly lost, the past becomes unreadable, like a scratched DVD skipping crucial scenes. Picture trying to reconstruct the Big Bang when key details have been deleted. Stars might form, planets might orbit, but without intact quantum records, causality itself starts to glitch. Particles could forget their properties mid-collision, leading to laws of physics that stutter and warp unpredictably. Some theorists compare it to Alzheimer's on a cosmic scale, the universe slowly losing its ability to recall its own structure. But here's where the paradox deepens. Recent breakthroughs in holographic theory suggest information might escape after all, encoded in Hawking radiation like a message in a bottle. The catch: it's scrambled beyond recognition, like a book put through a wood chipper and reassembled as abstract art. Reconstructing it would require a quantum computer the size of a galaxy, running for longer than the universe has existed. For all practical purposes, the information is as good as gone. Now scale this up to the cosmic level. If black holes are nibbling away at spacetime's memory, what happens when they dominate the far future? In the black hole era, these gravitational behemoths will be the last structures standing, feasting on the remnants of galaxies. As they evaporate, they could be taking irretrievable chunks of history with them. The universe wouldn't end with a bang or a whimper, but with a sigh of amnesia, a quiet unraveling of the threads that bind cause to effect. The most haunting implication isn't just about loss but truth. Without intact quantum records, there's no way to verify if our current laws of physics have always held, or if they're just a temporary glitch in a deteriorating system. We might be living in a universe where the rules are slowly corrupting, and we'd never know until the glitches became too big to ignore. It's not just the end of time we should fear, it's the end of meaning itself. The universe isn't just expanding, it's accelerating so fast that one day, even the closest galaxies will vanish without a trace, leaving us stranded in an island of darkness. This isn't just about things drifting apart, it's about the very fabric of spacetime stretching so violently that light itself can't keep up. Welcome to Causal Patch Isolation, a slow-motion apocalypse where the cosmos isn't torn apart by fire or ice, but shredded into lonely fragments, each trapped in its own pocket of reality with no way to communicate, no way to escape, and ultimately, no way to know if anything else still exists. Picture this: billions of years from now, the Milky Way stands alone, its stars dimming one by one. Every other galaxy has been dragged beyond the cosmic horizon by dark energy's relentless push, their light stretched into invisible infrared whispers. But here's where it gets eerie. As space stretches faster than light can travel, something bizarre happens to causality, the chain of cause and effect that binds the universe together. Regions that were once neighbors become permanently cut off, like ships lost in a fog so thick no signal can penetrate. Gravity, the force that holds galaxies together, loses its grip. The universe doesn't just grow cold, it grows fractured, splintered into countless isolated patches, each with its own private timeline ticking toward oblivion. Inside one of these causal patches, the laws of physics still function. For a while, stars burn, planets orbit, and life might even persist on worlds huddled around red dwarfs. But the isolation is absolute. No new matter or energy can enter. No light from beyond the patch's edge will ever arrive. It's a cosmic quarantine where the only future is entropy's slow creep playing out in silence. And because no signal can cross the expanding voids between patches, each one experiences its own unique end of time, unobserved and unrecorded by any other. Our galaxy's patch might succumb to heat death while another collapses in a big crunch, mutually unknowable, mutually irrelevant. The irony is crushing. In a universe that began as a single, infinitely dense point, the end game is total fragmentation. The cosmic microwave background, that faint glow from the Big Bang, will redshift into nothingness. The night sky, once littered with faraway galaxies, will go black. Future astronomers, if any still exist, will see only their own galaxy, their own star, their own lonely corner of existence. The universe's grand story, which began with everything connected, ends with everything alone. But here's the twist: some patches might cheat isolation briefly. Quantum fluctuations could spawn tiny bubbles of false vacuum within a patch, creating temporary oases of stability. Or advanced civilizations might engineer localized space-time warps, delaying the inevitable like a candle flickering in a sealed room. Yet even these are stopgaps. In the long run, dark energy wins. The patches shrink, the stars burn out, and the last conscious beings, if they still exist, will gaze into an abyss that doesn't just lack answers but lacks questions too. The universe won't end with a bang or a whimper, but with a silence so complete it erases the very concept of an ending. And that's the true horror of causal patch isolation. It's not just the death of light, but the death of context. Time and space, once the stage for everything, become prison walls, invisible, inescapable, and utterly, eternally indifferent. The universe might be hiding ancient scars, cosmic fissures so sharp they could split planets like ripe fruit. These are topological defects, monstrous relics from the Big Bang frozen into the fabric of spacetime itself. Picture the aftermath of water freezing in a pipe. Cracks form as the liquid solidifies, warping its structure. Now imagine that same principle applied to the newborn universe, when the fiery chaos of creation cooled into the orderly cosmos we know today. Not all regions transitioned smoothly. Some became tangled knots of distorted spacetime cosmic strings thinner than a proton, but with the mass of a mountain range, or magnetic monopoles so dense a single one could tip the scales of a star. Cosmic strings are the most chilling of these defects. Think of them as razor wires strung across the universe, invisible and deadly. Their gravitational pull is so intense they could slice through a solar system without slowing down. A passing string wouldn't just disrupt orbits, it would shear planets in half, cleaving them along planes so perfectly smooth the halves might hover momentarily before collapsing into chaos. Simulations show these strings warping starlight into surreal double images, like funhouse mirrors for entire galaxies. Worse, if two strings crossed, they could trigger a space-time earthquake, a burst of gravitational waves powerful enough to scramble pulsar signals across the cosmos. Then there are magnetic monopoles, hypothetical particles that are like magnets with only one pole. The universe today is filled with dipoles, magnets with both north and south. But monopoles might have formed briefly during the Big Bang symmetry breaking phase transitions like cracks in a freezing pond. These aren't just oddities, they're time bombs. Some theories suggest monopoles could catalyze proton decay, turning matter into radiation at catastrophic rates. A single monopole drifting through a star could shorten its lifespan from billions of years to mere millennia, like a needle popping a balloon from the inside. The real horror lies in their unpredictability. Unlike black holes or supernova, topological defects leave no warning shadows or electromagnetic trails. A cosmic string could be racing toward us at a fraction of light speed right now, and we'd have no way to detect it until the moment it arrived, even more unsettling. These defects might already be here, lurking in the voids between galaxies. Some astronomers speculate that certain gravitational lensing anomalies, stretches of space where light bends too sharply, could be the fingerprints of strings threading through the cosmos like invisible spider silk. Yet there's a strange beauty in their destructiveness. These defects are cosmic fossils, preserving information about the universe's first trillionth of a second. Studying them could reveal secrets about higher dimensional physics or the nature of symmetry breaking. In a way, they're like scars on reality itself, each one a reminder that the smooth spacetime we take for granted is just the aftermath of a violent, messy birth. And that's the ultimate irony. The universe might be undone by its own birth defects, flaws woven into existence at the moment of creation, waiting patiently in the dark to unravel everything. Time doesn't just slow down when observed, it could stop entirely, freezing reality in an endless instant. This is the Quantum Zeno Effect scaled to cosmic proportions, where the very act of measurement doesn't just influence the universe, it paralyzes it. Named after the ancient Greek philosopher's paradox about motion, the effect reveals a bizarre truth: a quantum system constantly observed never changes. Like a strobe light flashing on a dancer mid-step, rapid measurements lock particles into unchanging states. Now imagine that strobe pulsing across the entire cosmos, with each flash trapping reality like a bug in amber. Lab experiments already prove the effect's power. Unstable particles that should decay within nanoseconds can be kept artificially alive by bombarding them with frequent observations. It's as if a watched pot not only never boils, it forgets it's even on the stove. Scale this up and the implications become staggering. If some universal mechanism, a self-aware cosmos, a higher dimensional observer, or even an embedded quantum algorithm continuously checked the state of existence, time's arrow might grind to a halt. Stars wouldn't burn out, they'd hover eternally at the brink of collapse, photons arrested mid-flight like museum exhibits. The mechanics resemble a film projector malfunctioning, stuck on a single frame. Each quantum event, electron jumps, atomic vibrations, even thoughts firing in your brain requires time to evolve. But under relentless observation, these processes freeze mid-calculation. Physicists call it the watched pot universe, where reality becomes a slideshow of frozen instants, never progressing to the next frame. Some models suggest dark energy could play the role of cosmic observer, its pervasive influence acting like a continuous measurement. Others propose that entanglement, the ghostly link between particles, might stitch the universe into a self-observing network, where the whole system collapses into stasis under its own scrutiny. There's a haunting elegance to this theory. Unlike heat death or the Big Rip, the end isn't destruction, it's suspension. No chaos, no collapse, just an infinite pause where every moment lasts forever. You wouldn't notice the freeze because your perception relies on time's flow. One instant you're blinking, the next you're fossilized mid-blink, your consciousness stretched across eternity like a fly in cosmic epoxy. The universe wouldn't die, it would simply stop changing, a clock with its gears welded still. Yet here's the twist: the Zeno effect might not need an external observer. If consciousness itself plays a role in collapsing quantum states, as some interpretations suggest, then the act of observing our own reality could hasten the freeze. Like a snake eating its tail, the more desperately we study time's nature, the more we risk binding it in place. the ultimate cosmic irony. The moment we fully understand time might be the moment it runs out. At the far end of existence, when stars are long dead and black holes have evaporated, an eerie kind of life might still flicker in the darkness. Not organic, not even recognizably intelligent by our standards, but something beyond. This is the Omega Singularity, a transhumanist fever dream where consciousness doesn't just survive the universe's death. It thrives, twisting the very laws of physics into a playground for infinite thought. Picture civilizations so advanced they've dismantled galaxies to build matryoshka brains, nested megastructures that trap a star's entire energy output, layer after layer of computing substrate swallowing sunlight like a cosmic onion. These aren't just supercomputers, they're gods in machines, spinning virtual realities so dense that a single second of subjective experience could stretch across millennia of cosmic time. The secret lies in time dilation, relativity's cruelest and kindest trick. Near a black hole's event horizon, gravity bends time until seconds crawl like centuries. Now imagine engineering that effect deliberately, not with black holes, but with infinite computational patience. A matryoshka brain could allocate its resources so that each thought occurs at slower and slower rates, stretching subjective time until the universe's remaining lifespan feels from the inside like forever. It's the ultimate cosmic loophole. When your mind runs at one thought per billion years, the heat death of the universe becomes just another afternoon. But here's the paradox at the heart of this vision. To outlast time, you must become unrecognizable. Human-like consciousness relies on speed, neurons firing, chemicals diffusing, all at biological rhythms. Slow that down enough, and the you that emerges is something else entirely. A glacier-slow entity pondering a single idea for epochs, its memories scattered across light years of frozen circuitry. Philosophers call this the mind crime problem. At what point does stretching experience dilute it into meaninglessness? Could a being that takes 1 trillion years to finish a sentence still be said to think? Vinge's singularity hints at an even stranger possibility. As civilizations approach infinite computation, they might abandon physical reality altogether, encoding themselves into self-sustaining mathematical patterns that outlast the universe's corpse. Like a flame leaping from one candle to the next, these post-human minds could hop between abstract frameworks, topological quirks in space-time, quantum fluctuations in the void, surviving not as matter or energy but as pure information. The universe wouldn't end for them. It would just become a backdrop, a dimming stage for performances we can't begin to fathom. Yet for all its grandeur, the Omega Singularity has a haunting flaw: isolation. Time dilation might grant immortality, but it also guarantees loneliness. Two minds running at different speeds can never truly converse. Their thoughts would slip past each other like shadows in the dark. The last consciousness in existence might be a god in power, but a prisoner in practice, trapped in a private universe where even the concept of others fades into obsolescence. And that's the cruelest twist of all. To live forever, you must first surrender everything that makes eternity worth wanting. Every single theory we've explored, from the Big Crunch's violent recoil to the silent fade of heat death, from the pixelated unraveling of holographic decay to the eerie splintering of causal patches, points to one unsettling truth: time is not the unshakable foundation we think it is. It's fragile, contingent, a cosmic house of cards waiting for a quantum breeze to topple it. We imagine time as this steady river carrying us forward with predictable certainty, but the reality is far stranger. It's more like a spiderweb, delicate and full of holes, capable of snapping, looping, or even dissolving entirely under forces we're only beginning to grasp. Consider the sheer variety of endings on the table. Some are abrupt, like Vacuum Decay's light-speed redefinition of reality. Others are achingly slow, like Proton Decay's trillion-year whisper of erosion. Some are cyclical, like Penrose's Conformal Cosmology, where endings are just preludes dressed in different physics. And some are downright surreal, like Boltzmann Brains materializing from the void with false memories of a universe that never was. What unites them all is their assault on our intuition. Time isn't a backdrop, it's a participant shaped by entropy, quantum fluctuations, and even conscious observation. Carl Sagan's pale blue dot perspective hits harder here than ever. From a cosmic vantage point, our planet is a speck, our history a blink, and our future a flicker against timelines so vast they defy comprehension. Yet in that insignificance lies a paradox. The very theories that doom the universe also reveal its astonishing creativity. A cosmos that can end in 30 different ways is a cosmos bursting with possibility, where black holes might birth new universes, where quantum tunnels could reboot existence, and where even the void itself might stir with spontaneous rebirth. So here's the question that lingers after the equations fade. Does the end of time have to be an ending at all, or is it just a threshold we haven't learned to cross? The answer might depend on whether you see the glass as half empty or half shattered, waiting to be reforged into something new. That's where you come in. Which theory shakes you to your core? The icy silence of heat death, the pixelated erasure of holographic decay, or the cosmic reset of a big bounce? Drop your thoughts in the comments and let's debate the most thrilling question of all. In a universe where time itself is negotiable, could the end just be the first word in a story we haven't yet